Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to review all of the important components of a reinforcement learning system, specifically within the framework of MDPs or Markov decision processes. First, a Markov decision process is really just a collection of 5 things: the set of all states, the set of all actions, the set of rewards given a state action next state triple, the state transition probabilities, and the discount factor gamma. To recap, we'll make up some examples of all of these things. A state represents what the sensors of your agent would measure from the environment. So for example, in grid world, that would be your position on the board. In tic-tac-toe, it would be the specific configuration of X's and O's on the board. In a video game, it would be the pixels on the screen, and perhaps other inputs that tell you the number of lives you have left, your health, and so on. Although strictly speaking, if we wanted to make an AI as human as possible, it would have to infer that information through just the pixels on the screen. An action represents anything that the agent can do while in a state. For tic-tac-toe, that would be placing your piece somewhere on the board. In a video game, that's typically moving up, left, right, or down, or pressing an action button. Rewards are what you get at every step of the game. Remember that rewards are real valued, and the goal of an agent is to maximize the total future reward. Remember that we have to be careful about how we define rewards. If we have a robot trying to solve a maze, and we give it 0 reward at every time step, and 1 for solving the maze, then it's possible that the robot will never solve the maze, or solve it very inefficiently. This is because if all the robot sees are zeros, then it thinks that 0 is the maximum possible reward, and it'll infer that it doesn't matter what it does, since all actions lead to 0 reward. Another possibility is that it might learn to solve the maze, but only through random movements, since it has no incentives to solve the maze as quickly as possible. A better solution would be to assign a reward of -1 for every step. In this way, rewards are always negative, but remember, these are numbers on a real valued scale. The agent doesn't assign any connotation to positive or negative like we do. It's only trying to maximize a number. In other words, a total reward of -3 is better than a total reward of -300. So it's important how we define rewards. You'll see later that OpenAI gym environments actually assign us the reward. It's been debated whether or not it's a good idea to assign rewards other than the default reward that's provided. In real life, we would be assigning the rewards because we have to. There is no one else that will assign rewards to our agents. Next, we have state transition probabilities. At first glance, these might seem unnecessary. Consider grid world. If you press the up button, you should go up to the next square. This square should always yield the same reward. This seems deterministic, so you might wonder why we need to model this as a probability. The answer is that not all environments are deterministic, so the environment itself can be one source of randomness. Another source of randomness is that our reading of the state can be imperfect. It only reflects partial knowledge of the environment. To use an example we've seen before, consider this one frame of the game Breakout. From this frame alone, we can't tell if the ball is moving up or down. Therefore, the next state is not deterministic. This is also where Markov comes from in the term Markov decision process. As usual, when we say Markov, we usually mean first-order Markov, which means that we model the next state and reward probability as being dependent only on the previous state and action, rather than all previous states and all previous actions. Notice how the notation is a little funny. We use S prime to mean the next state at time t+1, but we don't say R prime, we just say R for the reward at time t+1. So the prime symbol doesn't necessarily mean at time t+1. Next we have the discount factor. The point of the discount factor is intuitive. We would rather get $100 now, rather than be promised $100 10 years from now. While we would like to maximize the total future reward, the farther and farther we look into the future, the harder it is to predict. There are a lot of things that can happen between now and 10 years from now. So maybe we should discount future rewards based on how far into the future it is. We call the discount factor or discount rate gamma. From this we can define the return. At every step of its existence, the agent tries to maximize its expected return. This brings us to the next concept, the value function. Because rewards are probabilistic and the return is a sum of rewards, then the return is also probabilistic. This allows us to define the expected return given we're in a state S, which we call the value function. The value function is an estimate of the return from this point onward. Recall that the state value function is usually denoted V of S, and the action value function is denoted as Q of S and A. We typically use Q for learning the optimal policy, which we call the control problem. Finding V of S or Q of S and A given a fixed policy is called the prediction problem. Remember that a policy is usually denoted by the symbol pi, and it tells us what action to take given a state. It can be deterministic or probabilistic. The Q function is better for the control problem because it's indexed by the action, so it tells us what the best action is given a state. We can simply take the max over all actions. For V of S, we can't do this. We would instead have to actually take an action, see what state we end up in, and then maximize over all the possible actions after having done them. You can see how this would be infeasible in the real world. Therefore, we always use Q for finding optimal policies. Another key concept is that of an episode. This is like one run of tic-tac-toe. Typically, our agent will need to play many episodes in order to learn the optimal policy. Tasks that have endings like this are called episodic tasks. Tasks that can last forever are called continuing tasks. The state at which an episode ends, or in which no further action can be taken, is called a terminal state. Because the value function is defined as the expected return after arriving in a state, and the return is the sum of all future rewards, this means that the value of any terminal state is 0.